I had, since I went to NYU, I had sort of balanced my research between global environmental change from fossil fuel burning, mostly the greenhouse effect, and trying to answer the question of whether it would be possible to run our high-tech civilization without fossil fuel emissions. Because it became very clear from the work that we had been doing, modeling not only the climate, but also the carbon cycle, which determines how CO2 will build up in the atmosphere from our fossil fuel burning, that at some point we would realize, political leaders would realize, that we have to phase out fossil fuel. You know, without the climate change challenge, a lot of people don't realize that, we would not have a crisis where we would need to change the energy system in a revolutionary way, probably until the 22nd century, because there's a lot of coal. I mean, we'll be out essentially of oil and natural gas, conventional oil and natural gas, by the end of this century, and we're probably at a peak rate of production right now in the case of oil, and soon will be in the case of natural gas. I mean, this is planet-wide. And so the 98 paper was the result of some conference that we organized, myself and my former student Ken Caldera, at the Aspen Global Change Institute, where we brought together a large number of experts in various kinds of energy conversion, everything ranging from carbon capture and storage in coal-fired plants to have the CO2 buried underground, to innovative kinds of nuclear reactors that would be relatively safe and proliferation resistant, and yet had fuel cycles that could provide energy for a long time and that would address the issue of waste disposal from nuclear reactors, and of course various advanced concepts in solar and wind energy. And that was the reason behind the paper and behind it. And what we realized is that it was important to show that we would need enormous amounts of energy in order to accomplish this kind of stabilization. We didn't realize that the challenge was as big as it was. And that continues to be an issue because there are people who continue to say that climate change can be dealt with existing technology on the shelf. We began to realize at this point that that wasn't going to happen, or that it could be dealt with well, there's a difference between conservation and efficiency, but more efficient sources of energy that would provide the same end use with less consumption of fossil fuel. And based on that conference, we wrote the paper in '98 that eventually was published in Nature, and that paper really found the opposite conclusion, that it would be an enormous challenge to generate the amount of energy we needed to run our civilization. And that challenge would come in the 21st century increasingly as the decades rolled by until the middle of the 21st century. And we also, in that paper, for the first time, I think, published our suggestion that we might need something like an Apollo program or a Manhattan Project in alternative energy to address this problem. And that was the genesis of it. Well, the basic problem is the issue of scale. I mean, let me just give you a couple of numbers from each of these three categories: coal, nuclear, and renewables. In the case of coal, I mean, the reason we're looking at coal is because it's the most abundant fossil fuel. It's also the dirtiest. So we simply can't afford to burn coal in power plants, which is what we do now. Most of the electricity we get now comes from coal combustion. But there's a lot of energy in it. So there is a technology that was proposed where you would gasify the coal, and the products of that gasification, which would be carbon monoxide and hydrogen, would be used to drive a very efficient system of power plants with steam turbines and gas turbines called an integrated combined cycle power plant. And there would be CO2 collected in a centralized location. That CO2 would be disposed of underground. The idea would be highly concentrated, it would be collected, and it would be buried deep underground. However, there is not in the world today, although there's a huge amount of discussion, a single integrated combined cycle power plant that collects the CO2 and puts it underground in deep saline aquifers, which is the proposal. There was a proposal under Bush to build something called FutureGen, but it was never built, and some people are trying to restart it now. And so we've had this tremendous loss since we've realized that this is a potential solution, that we really haven't done anything. This is why we emphasize the idea of Apollo program types but we need a bunch of Apollo programs. This would be one of them. In the nuclear field, we really feel that we have to get off these light water U-235 reactors. First of all, they're fundamentally vulnerable to loss of coolant accidents. That was the kind of accident that we had at 3 Mile Island. That was the kind of accident we just saw in Japan, where the fuel rods of the power plant become uncovered, where they have to be surrounded with a coolant that takes the heat and uses that heat to drive steam turbines. There are many other designs that are inherently much safer, gas-cooled modular reactors, for example, but particularly the fuel is not appropriate because there's less energy in U-235 that we've discovered than there is in gas and oil are gone by the end of the century. So we propose that we should be looking at thorium as a feedstock. Again, this is a long and perhaps too technical discussion, but that would be another Apollo program. In solar and wind energy, we need to seriously look at very large-scale deployments of solar panels, either photovoltaics or solar thermal, in deserts. We're not going to solve this problem with rooftop PVs. I mean, again, if you look at the problem quantitatively, the energy consumption levels in Western societies are simply too great. We might want to locate them in deserts in the U.S., for example, southwestern deserts, or in the African Sahara. So that's another Apollo program.